Okay, so in this lecture we start with the topic of cyclic subgroups. I will be trying to complete this whole topic in this one lecture itself, but if I'm not able to do so, I'll obviously bring out another lecture to complete the topic. Rather, let's start with it. So in the previous lecture, I had given an introduction to what cyclic groups are. So precisely, if you recall, we had discussed that if G is a group, let's say, so we have G as a group, and we considered a subset of G, and then we denote this to be the smallest subgroup, the smallest subgroup of G containing A. Okay, the smallest subgroup of G containing A, and there were two very specific structures were given to you. One of them was it was the intersection of all the subgroups of G, each of which contained A. Right, this was one very obvious structure. And the other structure we gave is that we considered a set which contains elements of the form a1 to the power epsilon 1, a2 to the power epsilon 2, till an to the power epsilon n, such that ai, um, so ai is, so each ai comes from a, each epsilon I is equals to plus minus 1, right? So this was the basic structure we had given, if you recall. What more we had, but we need to specify. Okay, let's specify this as well. So n is a positive integer. N is a positive integer. Okay, and then we eventually showed that this is indeed the subgroup, which we denote like this, and this was basically said to be the so this subgroup was what we said to be the subgroup generated by A, right? Then we say that if A is a singleton set, if A is a any singleton subset of G, then the subgroup generated by A is usually denoted like this, and this is typically called the cyclic group, or on a more general note, a cyclic subgroup, because we have already chosen a group and we are choosing this element X out from that group. So it's a cyclic subgroup generated by X. So we are going to study these sort of subgroups in this lecture. Okay. So one obvious representation of a cyclic subgroup is that, so let H be of this form. Okay. Then H will be the collection of all the elements of the which are powers of X, such that this n is a positive integer including 0. We don't actually need the inclusion of 0. We will be eventually coming to it. Okay, let's just make it Z itself. Let us not restrict it to anything, because we will eventually get a very a very standard form of such groups. Then we will be able to understand what these powers typically are or typically look like. Okay, so for now let us just stick to how we have introduced the cyclic group. So this is typically what we have. Okay, clear. Okay, so I'll obviously refer to my previous lecture before coming to this lecture, because there are some things which will help from previous lecture to understand this very lecture. For example, why I have chosen the power to be any arbitrary integer. So hint to this structure is given in the previous lecture. You can go and check it out. Okay. Now, to understand cyclic groups, what we typically need is the concept of the order of an element. So I had also defined what order of an element are. Let me just symbolically denote it like this. Suppose you choose any element from a group G, then we say that the order of it is D if x to the power D is equals to 1, and there does not exist any k less than D, such that x to the power k is equals to 1. In a way, D is the smallest positive integer. Yeah, so D needs to be a positive integer. So D is the smallest positive integer, such that x to its power is 1. If there is no such positive integer such that x to the power of that integer is 1, then we say that the order of x is infinite. Okay, that's typically the case. Okay, now observe the following, that Okay. So also so a few more things is that in this case we say X is the generator. X is the generator of H. Clear? Okay. Now, given the structure, observe the following. So H is written as x to the power n such that n belongs to Z. Now we can obviously also write it as x to the power say minus m such that m belongs to Z, where we have chosen n to be minus m. Okay. This is very obvious. We can do it obviously. We can choose, 2 to be minus of minus 2. Both are integers, right? But then this implies that h is nothing but the, it's generated by x to the power minus 1, because x to the power minus m is nothing but x to the power minus 1, that is the inverse of x to the power m. Right? So, so obvious fact from here is that if h has generator x, then the inverse of x is also the generator of h. Okay, this is the first observation. This is the first important observation we have. Another important observation, which is obviously very evident and very trivial from the structure of a cyclic group, is that every cyclic group is abelian, and this immediately holds from the law of exponents, nothing else. Okay, the powers are integers, so their addition will commute. So the law of exponents immediately says that the cyclic groups are abelian in nature. Okay, clear? Let us first consider a few examples which are very easy to understand. Examples. What can you say about Z? Is Z a cyclic group? Um, Keep in mind that Z is an additive group. It's not a multiplicative group. So, you know, so this were the notations which we have introduced for an additive group. In the previous lecture, I also stated simply the difference between the multiplicative representation and the additive representation of the subgroup generated by a set. Typically speaking, H is this. So this was the representation. So this was the representation in case of additive group. What happens in the case of, sorry, this was the representation in the case of multiplicative group. What happens for an additive group? So this will be just n times x, such that n is integers, right? So what we are typically doing in a cyclic group, we are composing, we are choosing an element which we say with generator. We are composing that element with itself, some integer number of times. That is what we are doing. So if you have an additive group, the composition is additive. If you have a multiplicative group, the composition is multiplicative. That's all. So recall that Z is a additive group, right? So any element you choose out of Z, you can write A as 1 plus 1 plus 1 and so on. How many times you need to add 1? You need to add 1 A times. So isn't it obvious that Z is the group generated by 1? And since minus 1 is the additive inverse of 1, so it's also generated by minus 1. Clear? Okay. Now you can also verify it by the two-sided inclusion as well. So this was one-sided inclusion, because if you choose any element from A, then it will be contained in this. Other-sided inclusion is obvious because this will be a subset of Z, because 1 is an element of Z. This is pretty trivial. Another important example which you guys have been working with for a long time, but we haven't expressed that as a cyclic group, which is if you consider D to N, then what is an arbitrary structure of D to N? So it is 1 R squared. It runs till R to the power n minus 1. Then you have S SR, and this runs till SR to the power n minus 1. Then observe, if I consider this set 1 R squared till R to the power n minus 1, isn't this exactly R? Sorry, the group generated by R by definition, because we know that R to the power n needs to be 1, right? So if R to the power n needs to be 1, so if I compose R to the power n minus 1 with R again, you get 1. And if you go on, then you start repeating the elements R squared and so on. So this is the only collection of elements you require, or you get. This is indeed a cyclic subgroup of D to N. Cyclic subgroup of D to N. Is it clear? Okay. Okay. What more can we say about examples? Um, okay. Let me just give you a very small exercise. Number three. What can you say? What can you say about Zn? Okay. That is Zn cyclic? Is Zn cyclic? If not, find its cyclic subgroups. Find its cyclic subgroups. Okay. So this is a very easy thing to do. Now, the obvious questions which arise from the concept of a cyclic subgroup is that what can we say about the finiteness and the infiniteness of a cyclic subgroup? What can we say about the subgroups of a cyclic subgroup? Or what can we say about the generators of a cyclic subgroup? Because these are the things which we need to keep in hand in order to get full information about a cyclic subgroup. Okay, so we are moving towards that direction. So we start with the proposition first. And the proposition is quite intuitive, quite obvious. You will be able to understand what I'm trying to say. The proposition is very simple. Let H be a group generated by X. I'm not using the term subgroup every time because I am arbitrarily not collecting a group first and then choosing an element out of it to form a subgroup. So if X is any element, this structure is indeed a group. Whether it's an element from a group or not, that doesn't matter. It's indeed a group on its own. So I'm just telling it to be a cyclic group. So let H to be a cyclic group generated by X. Then the cardinality of H or the order of H is same as the order of X. Let me not use this notation for the order of X. Let me use the standard notation, order of X. Okay. With if one side is infinite, so is the other. So is the other. Okay. So is the other. Okay. Okay. Specifically, what I'm trying to say is that. So let me just write the word specifically. The cardinality of H is say n less than infinity, implies x to the power n is equals to 1, and H is of the form 1x x squared till x to the power n minus 1. Okay. Number two, or let me not. Yeah, should I specify this at this moment or should I wait for a bit? Okay, let's do it at this moment. If later in any case we require such notations again, we will prove it again, no matter what. Okay, so this is the the structure of H. If H is infinite, then there does not exist any n such that x to the power n is equals to 1, and here comes the important part, that x to the power a cannot be equals to x to the power b for any a not equal to b in the integers, let's say. Okay. Yes, so these are the statements which we need to prove. Now, what will these statements typically do? So, if you have the order of an element, then you can get hold of the cyclic group generated by it. That's obviously that. If the order of the element is infinite, then the cyclic group is pretty easily formed by just choosing that element and keep composing it. Okay. If it's finite, then also we get a structure in hand, which is very easy to find. Okay. For example, let me just first explain this with an example. So we had discussed about the cyclic subgroup generated by R. R was the rotation in a dihedral group. Right? So we start with R. We know that the order of R is n in case of a dihedral group. So we know that the cyclic group generated by R will only consist of elements 1, R, R squared till R to the power n minus 1. And that is exactly what we had. Okay. So proof of it. The proof is The proof is fairly easy to do. Observe that. mm, okay, first thing first. See, these elements are easily acquired. That is the first thing. Okay. So first thing which we need to check is that are all these elements distinct? Okay. So let x to the power a is equals to x to the power b for b greater than and a and b both being less than n. Okay. But this means that x to the power b minus a is 1. Now if a and b are both less than n, then b minus a is also less than n, contradicting. So this contradicts the minimality of n, right? Contradicting the minimality of n. Because n is the least positive integer such that x to the power n is 1. B minus a is a smaller integer, smaller positive integer such that x to the power that is 1, which is not possible because n is the smallest integer to happen. So, small positive integer to happen. So, contradicting the minimality of n. So, that means this cannot happen. Thus, the elements 1, x squared till x to the power n minus 1 are all distinct. Now our second question is whether there can be more elements in this group. Okay. Okay. So let b be greater than n. Okay. Then there obviously exist integers q and r such that b can be written as qn plus r, with r being 0 or r being less than n. Yeah, this is simply the Euclid's division lemma. But then, so that implies x to the power b. So we are considering the elements which are powers of x with the power being greater than n, greater than the order of x. So x to the power b is x to the power qn times x to the power r. But we can write the first term as, because these are all integers, right? These are all integers. So we can write it as x to the power n whole to the power q dot x to the power r. Now x to the power n is 1. Right. So if x to the power n is 1, so this implies this is x to the power r. Thus observe, therefore the powers exist modulo n, right? Because b is congruent to r modulo n, and we get that x to the power b is nothing but x to the power r. Right? So all the elements modulo a are modulo n are are the only possible powers. So this makes sense that h is, so if you choose any power above n, we divide that power by n, we consider the remainder. The remainder must be sum of the elements from 0 to n minus 1. So that's it, right? Okay, so this is the proof of the first statement. That's quite obvious. Let's talk about the second statement. The second statement is also quite obvious because suppose a is not equal to b. Let b be greater than a without loss of generality. What happens if the integers, powers of x and in terms of a and b equalize? This means x to the power b minus a is equals to 1. This implies that order of x is finite, right? Because there exists a positive integer. If b is greater than a, b minus a is a positive integer. So there exists a positive integer, x to the power of which is 1, right? So if there exists a positive integer, then obviously by well ordering principle there must exist a least positive integer to happen so as well. Therefore the order of x must be finite, but that is not possible given the hypothesis that the order of x is not finite, right? So therefore which contradicts the fact that cardinality of h is infinite. If you're concerned about the proof of this statement, then it's quite easy to do. Because you can compose the element x to itself till you reach its order. And when you reach its order, the number of elements left that exactly gives you the cardinality of H. That is right. If when H is finite. If H is infinite, there is nothing to talk about. That's exactly trivial from statement. I guess it's clear. So the proof of statements 1 and 2, they immediately give you the proof of the statement. Right? There's nothing to worrying about that. Okay. So I guess it's clear. Okay. Now we are concerned about what can be the possible elements which replicate the property of the order of an element. Okay. So now what actually we are targeting to do is that we are targeting to find whether a subgroup, a cyclic group, has multiple generators or not. Whether it has a unique generator or it can have more than one generator. Now one obvious fact is that this question has an obvious answer, which is no, because we have already stated the fact that if X is a generator, then its inverse is also a generator. Okay, but our goal is kind of trying to state whether if X is a generator, then if whether any power of X which is not -1 is also a generator. That is, if H is this, then whether there exists some positive integer, some integer such that x to the power a is also a generator. Okay. Okay. So let me start with this proposition first. Which states that let G be a group. Let G be a group, and let X be an element from G. Let M and N be integers. If x to the power n is equals to 1 and x to the power m is also equals to 1, then x to the power d is also equals to 1, where d is the GCD of m and n. So that is what we actually need to prove. Okay, that if you have two elements, the powers of which equal 1, then the GCD of the powers, that also gets to equal 1. Okay, so the proof of it, this is also pretty easy to prove. So like we know the a very famous number theoretic statement is that if D is the GCD of M and N, then there exist integers, say R and S, such that MR plus NS equals D. Right? Right? So then what is x to the power MR plus NS? So it's x to the power D. Okay. But then we can write x to the power D as x to the power M whole to the power R times x to the power N whole to the power S. Now x to the power M is 1, x to the power N is 1, so this is 1. Right? This is quite obvious. Got it? Okay. Now what can, so if we have this in hand, then what can we say about elements dividing a certain order? So we can talk about a corollary of this proposition. If x to the power m is 1, then x to the power d is 1, where d divides m. Okay, because if d divides m, so I'm just giving this. So if d divides m, then the GCD of m and d is d. Right, the greatest common divisor of d and m and d is d. So we have just found out the fact here is that if x to the power m is equals to 1, so yeah, so we can bring out this from here itself, from the proposition itself, right? Or we do not even need this criteria as well. Yeah, so I'm not telling that we don't even need this as well, because if d divides m, then m can be written as d times s. So x to the power m is equals to, sorry, I guess okay, my bad, I stated this in the inverse order. Sorry, I meant to say is that if x to the power d is equals to 1, then x to the power m is equals to 1, where d divides. Yeah. Now it's okay. Now we have got it. This was what I wanted to state. Okay, clear? Okay. Now this is quite obvious to prove, right? Now, uh, let me talk about something more. Okay. Then what can we say from this observation? Whether if you are given the order of a group, order of an element. So uh, let order of x be d, right? Then obviously x to the power d is equals to 1, and x to the power m is also equals to 1 for all the multiples of d, right? This is a very trivial observation which we get. Right? Okay. Now we come up to a very important characterization of cyclic groups. What we try to do is that now see two very important groups and very useful groups are the group Z and the subgroups of Z in terms of Zn. Okay. What we are intended to do is that we are going to show that these cyclic groups are nothing but the additive group Z and some specific subgroups of Z. So, nothing but I actually mean is that they are unique up to isomorphisms. Okay. So, what I'm trying to say is that theorem any cyclic group of you know how should I state this? Okay, I should state it like this: any cyclic group of same order are isomorph. Okay, let me state it like this. Let me state it in this way. Yeah, cyclic groups of same order are isomorphic. Are isomorphic. Okay. Uh, More specifically, we can say the following. Number one is that if you choose a positive integer and x and y are cyclic groups of order n, then these are isomorphic. I will be stating what an isomorphism is. Okay, these are isomorphic. Number two, that any cyclic group of order n is isomorphic to Zn. And number three, any infinite cyclic group is isomorphic to Z. Okay, these are the things which I want to prove. Okay, so a quick statement of isomorphism. Okay, so to talk something about isomorphism, we need to talk about homomorphism. So let me give a brief introduction to it. We will be obviously handling these topics in the next lecture or the next to next lecture, but let me just state it here. So let G and H be groups. Let G and H be groups. Then an operation preserving map. Okay, let me specify the operations of G and H. Okay, so let G dot and H plus B groups. Then an operation preserving map phi from G to H is called a homomorphism first. Is called a homomorphism if it obeys the following property, that phi of G1 G2 is equals to phi of G1 plus phi of G2 for all G1 G2 in H in G. Okay, so what do we mean by operation preserving? So it's very easy to observe. Since G1 and G2 are elements from capital G, so they are composed using the multiplication operation. But phi of G1 and phi of G2 are elements from H, so they are preserved using, I should say they are composed using the additive operation. So typically, if I just consider them to be multiplicative groups, then we can state it as phi of G1 phi of G1 G2 is equals to phi of G1 dot phi of G2, nothing else. So it's sort of this is called a homomorphism. A quick example: let phi be a map from Z to Z such that phi of n is equals to 2n. Then observe what is phi of n1 plus n2. Then this is equals to 2 times n1 plus n2. So this is 2n1 plus 2n2. 2n1 is phi of n1. 2n2 is phi of n2. Okay, I hope now it's clear what a homomorphism specifically means. Okay, clear. A bijective homomorphism is called an isomorphism. Okay. A bijective homomorphism is called an isomorphism. Okay. The important aspect about groups which are isomorphic to each other, that is, there exists an isomorphism between them, is their group structure is same. Their group structure is identical. The elements may be different. The groups, as sets may be different, but the structure of the group is identical. The composition is somewhat similar. The elements behave in a similar way. Okay. The properties held by each of the groups are similar. Okay. Isomorphic copies are somewhat same as groups. Okay. They need not be same as sets, but they are same as groups because they have the same structure as groups. We will discuss more on this when we will be discussing about homomorphism and isomorphism in great details, and we will do that in some other lecture obviously, but we will surely do that. Whatever, so how can we show that? How can we prove statement 1, 2 and 3? So to state statement 1, 2 and 3, we need just a map to show that the map is a bijective homomorphism, nothing else. So we come to the proof or proposition. Proof number 1. If I consider the map from the cyclic group generated by X to the cyclic group generated by Y such that X to the power K is sent to Y to the power K, then observe that we can get hold of an isomorphism. Okay, clear? I leave this to be an exercise. Okay, so left as an exercise. Left as an exercise. Try it on your own. We prove statements 2 and 3. Indeed, if you prove statement 2, then you can obviously get hold of statement 1. So what's statement 2? So what we typically do is that in statement 2, what we do, we map, we choose a mapping from say Zn to the group generated by X such that N is, or I should say K is mapped to X to the power K. Now, first thing first, this mapping is obviously surjective. Reason being, we have just seen that the elements in the cyclic group generated by X, where order of X is n, are the elements x to the power 0, which is 1, then x to the power 1, x to the power 2, till x to the power n minus 1. And these powers are exactly the elements in Z. So this map is surjective. You can obviously prove that. Okay. Is it a homomorphism? What is phi of K1 plus K2? So Zn is an additive group, right? So it's x to the power K1 plus K2. But x to the power K1 plus K2 is x to the power K1 dot x to the power K. By the law of exponents, x to the power K1 is phi of K1, x to the power K2 is phi of K2. Sorry, phi of K2, and so it's indeed a homomorphism. Is it 1, 1? Is it 1 1? So let phi of k1 be equal to phi of k2. Then that implies x to the power k1 is equal to x to the power k2. So by definition, it's obvious from definition. Then what can we say about, so this implies that x to the power k1 minus k2 is 1. So let k1 be k2 greater than k1 without loss of generality. Okay, but k1 minus k2 is an it's a positive integer less than n, right? It's a positive integer less than n. N is given to be the order of x, so there cannot exist a positive integer smaller than n such that this happens. Okay, so but k1, okay, I have chosen k1. Okay, so k1 to be greater than k2. Okay, but k1 minus k2 is less than n, provided the fact that both k1 and k2 comes from the Zn, right? So k1 minus k2 is less than n. So therefore it must be 0. So k1 minus k2 must be 0. That is the only possibility left. So that implies k1 must be equal to k2. What is Zn? Zn is the set of elements 0, 1, 2 till n minus 1. Whatever. So it's 1, 1. It's surjective from the fact that these are the only powers of x you get in the cyclic group generated by x, provided the order of x is n, which we have proved just back, right? Therefore, phi is an isomorphism. Okay. Now the case is quite easy. See, I'm just showing the intuition behind it. I'm not proving it right now because we will prove it in some other lecture. If A, B, C are groups, A is isomorphic to B. This is the symbol we use for isomorphism. That is, exists a map between A and B, which is an isomorphism. So if A is isomorphic to B, B is isomorphic to C, then observe that A is isomorphic to C as well. The basic intuition behind this is that if the group structure of A and B are same, and the group structure of B and C are same, then indeed the group structure of A and C is also same, right? Indeed, this seems some sort of an equivalence relation, because these are basic intuitions. We are not going into the mathematical rigor of this, but this is very basic intuition that every group will be structurally same to itself. So every group is isomorphic to itself. If A is isomorphic to B, that is the group structure of A and B are similar, then obviously the group structure of B and A are also similar in words. That means B is also isomorphic to A, and transitivity also. So the relation of isomorphism between groups is sort of an equivalence relation. Okay. So phi is an isomorphism. So now it's obvious that, so if I try to claim statement 1 using this, so x is isomorphic to Zn, and y will also be isomorphic to Zn if y is another group generated by y which is of order n. So indeed these two are isomorphic. So proving 2 indeed proves 1, but I left as an exercise to prove 1 independently. Okay. What about the third statement? So in the third statement as well, you choose a map from Z to this such that any integer n gets mapped to x to the power. Clear? Okay. So we map x to n to x to the power n. Now the statements of the proof are quite similar. Okay. So this is indeed an injective map, because if you choose x1 to be equals to x to the power n1 to be equal to x to the power n2, then that typically means x to the power n1 minus n2 is 0, sorry, is 1. But obviously such a positive integer cannot exist, because in this case we have assumed the order of x to be infinite. So if the order of x is infinite, there cannot exist a finite positive integer such that x brought to its power is 1. Okay, so this cannot exist, as order of x is chosen to be infinite. Therefore the only possibility is that n1 minus n2 must be 0, or n1 must be equals to n. So it's indeed injective. Surjective map, it's indeed surjective from the definition, because for all x to the power n in this, we get we get a power, because x is fixed in this case, right? The only thing which varies is n. So we get hold of an n which is in the set of integers. So we can map this n to x to the power n, right? So it's indeed surjective. And the concept of homomorphism, it directly comes from the statement 2, that what happens if you add two integers in z. So this gets mapped to x to the power n1 plus n2, but x to the power n1 plus n2 is nothing but x to the power n1 times x to the power n, right? So phi of n1 plus n2 is equal to x to the power n1 dot x to the power n2. This is phi of n1. This is phi of n, right? So in this case as well, phi is an isomorphism, right? So thus, just choosing a positive integer n, Zn gives all possible cyclic groups of order n. Therefore, the two fundamental classifications of cyclic groups are Z and Zn, right? Because every cyclic group of order n is isomorphic to Zn, and order infinite is isomorphic to Z. Clear? Okay. So it's already a 40 minutes long lecture, so I end this lecture here only. It will take one more lecture only to complete the concept of cyclic groups, and then we will move on to the concepts of quotient groups and homomorphisms. Okay. So meet you guys in the next lecture.